pointed in one direction. That's not always a state that we can measure directly. A lot of times we need to make lots of measurements, sometimes in the thousands, and then find the probability of states if it's in a superposition. Also, a key concept of entanglement, and I think Schrödinger said entanglement is the key of quantum mechanics. It's what makes quantum mechanics quantum mechanics. This basic circuit creates a pair of entangled qubits. And so, if we have two entangled qubits, when we change one, we do actually notice a change in the measurement of the second, which is also quite impressive. As for the general advantages of quantum computing, it's speed. Because of the superposition, we can almost view it as we are completing many different computations at the same time. Also in terms of complexity, because we have a superposition, usually of just zeros and ones, adding a qubit gives us 2 power n more possibilities, rather than when we add bits, we just have one more possibility for computation. And this is important. We use it for optimization, for factoring, not for multiplication. Because for multiplication, we can just perform one multiplication with a classical computer, and our algorithms are already very efficient. But when we have a probabilistic, let's say, analysis of the results that we gain from a quantum computer, multiplication isn't really beneficial for us in this case. These are some different physical realizations or hardware implementations of quantum computing that I'll try to go over briefly. So this is the, let's say, the big picture of topological quantum computing, which Dr. Raditya works on. The qubit here, or the built-in block, is the Majorana fermions. As for NMR, the qubit is the nuclear spin of the individual atoms, and we use radio frequency to control and read our qubits. The ion trap, we have ions trapped by using lasers, and the electronic states, for example, plus minus in the cations and anions, that's our qubit. For confined atoms, we have optical lenses focusing on one specific place, and that becomes our qubit. And this is what we're going to be talking about today, inshallah. Superconducting electrical circuits. Now, why superconducting quantum computing? As a brief history, there was a lot of development in superconductivity in the second half of the 20th century. And so superconductivity was very well understood. And so when the idea of quantum computing started, let's say, growing, the implementation of quantum computing on superconducting devices hit really impressively. Especially with the idea of the Josephson junction that we know from superconductivity, we were able to reach milestones. Pretty much every breakthrough in quantum computing, especially in the earlier part of quantum computing, was in superconducting quantum computing. Also, because we were very good at fabricating superconducting devices, it enabled the, let's say, speeding of the fabricating of actual quantum chips. That sped up things a lot. And the leaders in the world, honestly, are IBM and Google in terms of quantum computing. Even better than pretty much all universities worldwide. And IBM have a very good initiative under the name of Qiskit, which is I mean, they define it as a Python library, but honestly, it's almost like a school of quantum computing. It's impressive and a key starting point for anyone interested in the field to go and build some basic circuits and kind of experiment with it. So this is okay. Cavity QED. QED here is quantum electrodynamics. It was understood before the, let's say, the idea of circuit QED. The idea is, well, we have one specific photon in a state, and I'm sure we all, or most of us, know the Stern-Gerlach experiment. And so, applying a similar concept, you can have an up photon and a down photon. We can split them into two. What was noticed was that when we try to implement this cavity QED onto a circuit, the physics is almost identical, which is impressive to think about. And this is one individual photon. This is a macroscopic object which has Avogadro's number of atoms all together. But with a qubit, we want to have a two-level system. And the problem with implementing a harmonic oscillator, the gaps between energy levels would be identical. And so we know that the energy is h bar omega m plus half. So the difference between them is related to omega, the same omega. And so when we try to manipulate this system with a photon, for example, of frequency omega, what we end up is exciting this state to the next, this state to the next, and so we have infinite excitations. We cannot really manipulate the system. And so what we do is we alter our system to an anharmonic oscillator. And with the anharmonic oscillator, the gaps between each successive energy levels are different. And so we know this exact frequency and this exact frequency. And so what we do is we send photons, for example, with this frequency. And so we have only one excitation. And so we have a two-level quantum mechanical system of just 0 and 1 that we can call as 0 and 1, rather than having infinitely many states that we can't really deal with. And how we apply this, because we know that an LC oscillator can act as a harmonic oscillator. And so what we do is we change it to a nonlinear LC circuit. The nonlinearity comes from the inductor. So we change the inductor into a nonlinear inductor, which we call a Josephson junction. And all we need to know for today is that the nonlinear inductor is a superconducting inductor. We can almost view it as. And so this begs the question. Okay, we have now our qubit. It's just an LC circuit with nonlinear inductance. So how do we deal with this qubit? How do we interact with it? How do we read the state? And this is where CPW resonators or coplanar waveguide resonators come into play. Okay, so because we have inductors and capacitors as circuits in terms of our implementation of the qubit, each qubit has specific resonance frequencies that we can use to help identify our system. But when we try to measure this state, it doesn't really make sense to send one specific frequency, because sometimes the noise in the environment alters this resonance frequency. So for example, if you have a resonance frequency of theoretically 5 gigahertz, in practicality it might not be exactly 5 gigahertz, it might be slightly higher or slightly lower. And so what we do generally when we make measurements is we send a sweep of frequencies. So many different frequencies with small iterations between them, let's say. And so for this case, we use a harmonic oscillator, a normal LC circuit, because in this way it's just easier to fabricate, easier to deal with as well. And this is, let's say, a typical design of a coplanar waveguide resonator. And so we use them for reading, for controlling and manipulating our qubits as well. They're not just, there isn't just one application for them. And they began out as this, let's say, design. But we noticed quickly that if we're going to have many qubits on one chip in a small confined area, this is very impractical. I mean, I think I have, okay, we'll go on to this later. This can be, for example, 30 millimeters long. It's small, but if we want to have, for example, 1 million qubits, we're going to need to have a pretty big area for it, which we don't really want. And so what we do is we almost like squish this design into this. And so it's the same physics, the same slightly different fabrication process, but we noticed that we can have this, which maybe in the millimeter range long, we can have it into the nanometers. And so it becomes for a much more efficient and much more compact space. When we measure the qubits, or we attempt to either measure or read and control the qubit, like I said, we send different frequencies, and we analyze the results that we get. This results generally in the form of S parameters. I'm sure for those with juniors and seniors, we took it in 305 and 306. But basically, the S parameters are parameters that help us understand the physics inside the system. So we have transmission, reflection from both sides. And so we have 4 parameters for a 2-level system, we can say, almost. And this, so we would get plots like this of the voltage or the gain or the intensity versus the frequency. And the sharper the peak, the higher what we call the quality factor. Almost like the more ideal of a case is, because we expect to have one single peak of resonance frequency. And so, ideally, this is a result that we would get. It's very narrow peak, very sharp. Now, in the summer training, in my defense, I only had 2 weeks to design, but I got something like this, which isn't really good or meaningful, but it helps, let's say, shed light on the complexity of the whole understanding of the design of the coplanar waveguide resonator. It's not a simple case. yes, we go from a more complex into a simpler in terms of the applicability, but it's still relatively complex in terms of one, the design, and two, the fabrication, the making of it experimentally, which needs clean rooms and all sorts of instruments and devices. Now, okay, to go back slightly, because we have this issue, and sometimes these aren't really, they're not ideal in any way, shape, or form. And so, me and Dr. Sadim Rao, actually, well, Doctor came up with the idea, and I'm helping him implement it, inshallah. What we're thinking of is almost like fabricating our typical coplanar waveguide resonator with SAMs on top of them, self-assembled monolayers. What this does is, it helps fix this major issue. So if this is our coplanar waveguide resonator with these are the microstrips and this the bit in the middle, we have interactions with the air in different parts of the whole circuit, and so in practicality, the major cause of let's say the imperfection in the measurements is the interaction with the air between this circuit and the noise and the pollution. And so what we do is we thought that rather than having it be a random process where we send photons, for example, of 5 gigahertz, and well, some of them interact with the air because it has oxygen, nitrogen, hydrogen. What we do is almost like a poison pill of sorts. You can say we poison our circuit with something that we know the frequency of. And so what we have is one specific frequency for our qubit that we can control, and one frequency for this SAM, rather than having a plethora of resonance frequencies in the air. It's really hard to measure the pollution in the air, and because there are so many different compositions of particles in the air, it can cause a major headache in the measurements. And the beauty of this is we can almost like dope our entire circuit, not just the qubit. And so the frequency, the quality factor of the measurement increases for both the qubit and the whole circuit, the coplanar waveguide resonator, for example. So in conclusion, to sum up, we talked about the difference between quantum classical computing with brief emphasis, and what I want to highlight here is that the best, or the reason why there's so much investment, and sometimes in the billions of dollars in it, is because it helps solve two main issues, quantum computing. Firstly, it helps us in the speed and in the complexity of our algorithms. The speed, obviously, because of the superposition, but also because of the superposition, and in some cases the entanglement, it allows us for let's say, manipulation of qubits in ways that we couldn't usually manipulate our bits. And so it allows us to solve more complex problems more efficiently, and sometimes it allows us to solve problems that wouldn't be usually solved with the classical computer. Also, yeah, the way that we do this computation is with circuits and algorithms, as with any form of computation. But because it's so new, so novel, there's so much emphasis on quantum hardware. Actually, I was listening to one of the heads in IBM quantum computing and saying almost 80% of quantum computing jobs, 80% are in the hardware, with only 20% in the software and in the theory side of things. As for quantum supremacy, I know I'm just an undergraduate student, but we hear a lot of almost science fiction, pop science related to quantum computing. It's still got some way to go. Maybe in 5-10 years, sure, but it's not going to be, it's not just around the corner like many companies and research universities make it out to be. And yeah.
Thank you very much. Let's have a question, please. 5 minutes we can get.
Yes, I will start with 2 questions, very quick. First, I'm going to use your words. You said superconductivity is well understood. Can you tell us, for example, material that is superconductor?
Well, in the context of quantum computing, when we want to implement it on hardware, usually all we need is a Josephson junction. And so usually, typically what we do is we use neodymium because it has a higher critical temperature. Maybe, I think 10 to 15 Kelvin. And usually we operate the quantum computers in millikelvin scales. So it's far away from the critical temperature. So we don't really need to dive deep into the theory, let's say, of superconductivity. The basics that we get of just a simple judge's injunction, that's more than enough for our application here.
So for audience, up to now we don't have superconductor material at room temperature.
Yes.
Up to now we don't have it. Okay. There's one question about the anharmonic potential. Can you just put? So if you want a harmonic, how it looks like?
It would be something like this. So the gaps between each energy level are identical. H bar omega.
And here the gap is between each level is identical. So what's the difference?
No, here it's not. There's a slight change. As you can see here, they are smaller than at the bottom.
Sure. The equation in the top is E plus half.
This is
Is this
new.
what-
Yeah.
Hmm?
This is new. It's not the typical omega, but yeah,
So it's anharmonic.
The equation here may seem like a harmonic, yeah, but this is the essay.
Okay. What's the difference between the bottom of the well potential and the top?
They're just different energy levels. So here, n equals 0, 1, 2, 3, 4,
So do you
5,
think
6,
it's harmonic at the bottom, and as I go up, it's become anharmonic?
No. Usually it's anharmonic. There are small changes here that become more noticeable as you go up. But it's this equation is misleading.
Okay, thank you.
Probably my first question is about why we want a superconductor and supercomputer. Sorry, a superconductor for supercomputer. Can we imagine a classical system? So you are talking about having infinite number of states, right? Can we imagine a classical system with, let's say, any vector that points in any direction? So we have the theta and phi, the same way you have here. So it's classical at room temperature and doing exactly what you are doing.
This would be great ideally, but the problem with that is, while it solves one side of the problem with the box here, it becomes almost impossible to apply the superposition and entanglement.
Why? What prevents you from that? You have exactly the same thing. You have exactly the same, let's say, wave function, if you want.
I'm not sure
But
about
just
the
classical.
I'm not sure about the wave function, but we know that in quantum mechanics we need to have very small systems in order to apply the rules of quantum mechanics.
I will not apply the rules of quantum mechanics. It's still classical. I'm saying classical system, but it has an infinite number of realization. Theta and phi is the same as in your case.
I'm not really sure how we can translate the superposition and entanglement concept into a classical system.
Okay. The second question is about the noise. You are saying that there is a noise that is coming from air and all the polluting molecules. Are you sure it is what is considered in the literature?
Yeah, that's one of the main problems with it, actually. That's one of the main reasons that people are trying to actually think about different implementations of quantum computing.
There is one thing that in quantum transport that we call the shot noise, and the shot noise is something that is intrinsic to the transport, and it has nothing to do with the external environment. It's just something due to the charge which is quantized. So probably are referring to this, to the shot noise, which gives you randomness in the measurement of the current.
That is true. The shot noise side of things and the general intrinsic quantum nature of the system makes it, let's say, very prone to decoherence. But this isn't an issue that we can fix, really. It's almost like innate. It comes with the whole package of applying quantum mechanics. But this is something that we can manipulate, and there's a lot of work. I'd say that most, let's say, in the past 3 years, most journals or most papers published in the case of superconducting quantum computing are related in one way or other to this, either in the form of measurement or attempting to apply new materials or new ways of manipulating the hardware to reduce or to increase the quality factor, reducing the noise.
We have a 1 minute question, then we have to another speaker.
So one thing I would like to add is, it's not air, it's air interface. It's a material interface with air, not the air.
Yeah, but is it chemical interaction So, or it's just like time-dependent environment effect.
Quantum states with amorphous being. Quantum states with amorphous being.
We go ahead.
Yeah,
with
so,
your question.
so for me, let me just ask a conceptualization on that. So at the beginning, you actually had mentioned that, okay, with superconducting circuits, so normally you don't want to encode your qubit in a harmonic oscillator, but rather in a circuit comprising of a capacitor intersection junction. So that is usually called transmit. So there are also other types like a fluxon, squid, and so on. But can you maybe tell like what's because you haven't really told this before in your presentation. So maybe can you tell like what are the difference between all these different circuit realizations and like maybe the advantages and disadvantages.
I'm not really sure about them. I know I've read about them in general, mainly the transmon qubits.
Right.
And I know that it's most commonly used, especially in the IBM quantum computer. But the difference between them, I'm not really sure.
Okay, so maybe just transmon and fluxon. What's the difference between the two?
Also, I'm not really
Oh,
sure.
Thank you very much,
Yeah.
Umar. We have to go another webinar. So our next speaker